Hi, everyone. I am back, and apologies for that bumpiness. Thank you, Marco, and thank you to all the organizers for having me. What I want to do is I want to tell you about the work that we've been doing at Georgia Tech and Facebook AI Research on Habitat, which is a simulation platform for embodied AI. But before I get started, I just want to say, I've given a few of these talks, some of them pre-recorded, some of them live. The best part of them is the interaction with the audience. I'm also teaching a class online at Georgia Tech this semester, and I tell my students that, feel free to interrupt me at any point of time. The value that you gain from this live interaction, you're here on the Zoom call, might as well just interrupt me. I have plenty of recorded things available online, so the value here is the interaction. So please feel free to interrupt me. Okay, so I want to start with the embodiment hypothesis. This is a wonderful paper from Linda Smith and Michael Gasser from 2005, which states that the embodiment hypothesis is the idea that intelligence emerges in the interaction of an agent with an environment and as a result of sensory motor activity. This doesn't take much convincing for this audience. You're already, the assistive computer vision and robotics sort of efforts, but you're aware that there is somewhat of a change happening in the community where there is an increasing shift from disembodied AI systems to embodied AI systems. By disembodied, I would refer to static data sets captured from the web, typically of images, videos, text. And by embodied AI systems, I would refer to agents acting in environments. And there's two broad families of these agents and environments. The first one, as your workshop title suggests, are physical robots. Physical agents taking actions in the world, talking to humans in natural language. So things like, a human asking a robot, is there smoke in any room around you? The robot might be on a search and rescue mission. The robot can answer like, yes, in what room? And the human might say, go there and look for people. This is we're all aware of this, but there's actually a second case for embodied AI as well, where the body is not the AI system, but the body is the human. So think about a smart pair of glasses that a human is wearing, and maybe the glasses also have projection capabilities. These devices don't exist, but we're sort of thinking a decade or two ahead out where these things might be common. And then you can start to have smart personal assistants still observing from an egocentric perception. So virtual agents on smart glasses taking virtual actions, still talking to humans in natural language. Like, where did I leave my keys? So it's on your coffee table. Okay, show me the recipe for guacamole, and here's the recipe for guacamole. And as I'm making it, oh, by the way, you missed this one step, and you can get feedback back from this smart system. So both those I think of as agents acting in environments and as embodied AI. There are a few challenges as soon as you have to move towards this transition. Egocentric vision is not well curated at all. You do not get these well curated snapshots from the internet with their selection bias from the photographers. You see everything just as a unsteady stream of information. This is both a challenge and an opportunity, though. The opportunity is active perception. The agent controls the incoming data distribution. Your actions have direct consequences on the types of images or observations that you observe. And so in some sense, there are no bad views in embodied AI because you can simply change the view. The third thing, of course, which is what the reinforcement learning community studies strongly, is the notion of sparse rewards or sparse supervision. In most of the tasks that we define in computer vision, classification, detection, segmentation, depth from single image, mesh prediction, whatever you may have, you have an input, and as soon as you make a prediction, all counterfactuals and other things you could have said are also pre-enumerated, and you get full supervision on every reward and loss of saying everything else that you could have said. That's just simply not the case in embodied AI. You have to take a sequence of actions, and typically in the end, you know whether you succeeded or not. And yet, yes, of course, there is dense rewards and you can do reward shaping and things like that. But it doesn't really change the fact that as soon as you have a sequence prediction problem, this idea of understanding all counterfactuals, everything else that you could have done and said is simply not the case. That's not what we deal with. Okay. And of course, there is the grounded language understanding aspect of things. You want agents to understand, to see things around them and to be able to understand what people are referring to. So the common theme here for both these systems, whether it's a machine with a physical body or the human that has the body, is that either in a lot of these cases, this hardware simply doesn't exist, or even when it does exist, training and testing in reality is slow, it's dangerous, it's expensive, and it's not easily reproducible. It's slow because just the iteration cycles of testing on a physical platform, as anybody working in robotics can attest to, it's just slow. These machines, if they're big enough, can cause damage to themselves and things around them. They're often expensive. And the dirty little secret in robotics is that robotics experiments die when the person, the one grad student in the lab who knows how to make that robot work, graduates. It's not, this is the problem with reproducibility in robotics is not just that these things are hard to reproduce across labs or universities. Sometimes experiments are hard to reproduce if you move the robot from one side of the lab to another. And that is simply not how we can hope to make progress in these areas. And so for these reasons, we're not alone in this, but others in the community have also converged on a common solution, which is let's conduct large-scale, cheap, controllable trials in simulation, and then we'll fine-tune them or adapt them to reality. So we will train either navigation systems or interaction systems or perception systems or planning systems in simulation, and then we will deploy them on real hardware platforms in reality. And this is the broad group of collaborators that I'm here representing. This is the effort of Habitat. It's a platform for embodied AI research. And some of the engineering support, a lot of the engineering support for this is provided by Facebook AI Research, but I want to mention that this is a multi-year, multi-institution open effort. So this is not just a Facebook project. And our goal really is to create the ImageNet, COCO, VQA of embodied AI, and Pascal as well. What these efforts before us did very well is they gave to the community a data set, a task, a competition with a metric, and we could track progress. And I think that's what's missing in a lot of robotics and embodied AI problems, where it's not clear what is the standard data set, what is the standard simulator, what is the task that we're solving, what is the challenge that we can get towards. And that's been our vision in accomplishing these things. So there's in some of the things that we do, there's sort of like a 3-layer hierarchy of capabilities and things that we want to do. At the bottom layer in this software stack tend to be 3D assets that we render and simulate performance in, simulate agents in. Then there are simulation capabilities, and then there are embodied AI tasks that we can study. And so let me just give you a few examples of these. There are a number of 3D data sets now. Matterport 3D is one, Replica is another, ScanNet is another, Gibson is another. These are all scanned indoor environments, and 3D scanning technology has come along a long way. This, for example, is the Replica dataset from Facebook Reality Labs. This really is the state of the art in 3D reconstruction technology. So you can see how detailed the reconstructions are. Notice that there is reflection on the mirrors, because the mirrors so the glass surfaces are accurately reconstructed. We've done this, they've gone out and scanned this for multi-floor homes as well. So you can now see the geometry, and there's also annotation of the semantics. So all the objects are annotated. And so you can fairly easily generate data sets of, single image to semantic segmentation, single image to surface normal, single image to meshes, because we know all that information. And I wanted, this may not be, not a lot of people may know this, but 3D reconstruction technology is now a commercial offering. So this is the Matterport camera. It's a $3,000 device. You place it at various locations. It takes RGBD panoramic images, and you upload that data to a cloud, and you can just download this scanned mesh of that indoor space, which can be loaded up into habitats to conduct new experiments. So really, we're getting to that point where getting access to 3D scans is now as easy as, it's not as easy as taking a picture with your phone camera, but it is getting close to that. You do not need access to any special software skills or capabilities. We also support loading in of object datasets. So this is the popular YCB dataset, which contains common tabletop objects, and these can be loaded up into Habitat as well. And of course, we now also support a synthetic dataset and multiple such synthetic datasets. So this is a replica CAD, if you will, where we gave the replica apartment that I just showed 2 slides ago to artists to recreate it from scratch. And the benefit of doing this with artists is that now these objects are individual interactable. You can pick up mugs and things like that. And I also want to mention that existing data sets like Unity scenes from Thor and Robothor are also loadable in Habitat. So we're a platform. We support loading of multiple kinds of assets. I want to mention a few capabilities, but before I do that, let me see if there are any questions that anybody had asked. It just says, please post your questions. Okay. So here are some capabilities that I want to mention that Habitat has. Of course, we can simulate navigation. So a robot navigating in an environment, RGB, depth, surface normals, we can obviously do that. But we've also recently put in rigid body physics. So we can import in those YCB assets that I talked about. We can enable gravity, forces, pushing of things, poking, rolling of objects on the floor. We can do intuitive physics experiments where you can have objects disappear behind a wall and have an agent predict whether that's plausible or not. We also have articulated robot support. So this is a KUKA arm that we can do end effector control of. There's both dynamic and kinematic support. We also support legged robots now because we put in URDF support. So any robot that you can describe with a URDF file can be imported into Habitat scenes. We haven't hooked this up to low-level controllers yet, so you just see my colleague, just turning the joints, the joint kickback on and off. So we're not actually controlling the robot, but it's there to be controlled. And of course, you can see that there's multi-agent support. You can have multiple robots. Okay. So what research tasks do we study? So we actually have a library called Habitat Lab, which is a high-level Python library, which can be used to study a number of navigation, question answering, and instruction following tasks. So for example, this is the object navigation task where you're given the name of an object and a robot has to go find that object. So sofa, that's all you'll be told. This is the room navigation task where you'll be given the name of a room and the robot has to go find it. And we have papers appearing at ECCV on room navigation. This is the instruction following task where you're given turn around, go out the bathroom, turn right and go to the brown door. And this is of course the question answering task. And with collaborators, we have papers appearing on all of these tasks. Here's something that people may not know is capable, so that this scenario that I showed, so now we can in Habitat do things like these. So we can do the clean up the kitchen task. So we can pick up objects, put them in the sink. Right now, this is manual demonstration. This is a human with a mouse pointer clicking on an object, picking it up and putting it in the sink. But you can think of these as expert demonstrations to train an RL system with. And these are now also possible in a controlled manner in simulation. As you can see, these are not as photorealistic as the scans, but they allow for interaction. You can open up cabinets and you can put things inside cabinets and you can do collision checking, and the meshes are geometrically quite accurate. Okay. One thing I want to do as I structure my talk is to ask the question, what is a simulator for? And I see in the literature 3 different use cases of why people use simulators, but I don't see anyone clearly delineating their thought into orthogonal factors. And so I think of these as 3 orthogonal use cases or independent use cases. One use case of a simulator is that you want to train in simulation, that you want to use simulation as sensory motor experience generation. And it says nothing about what you want to test in. Maybe you want to test in reality, maybe you want to also test in simulation. The second use case is you want to conduct tests in simulation because it's a stand-in for reality and you want to test a hypothesis. Your hypothesis could be of the kind that model A works better than model B, or my idea for this type of memory or mapper or planner helps. And then you're testing that hypothesis in simulation because you can control certain things in simulation. Notice that these are orthogonal. You could, for testing in simulation, maybe you trained in simulation, or maybe it's not even a learning-based algorithm. You are simply programming a planner, and that's fine. And the third is agents mental simulation. And here I will repeat a quote by Kenneth Craig, which is, if the organism carries a small scale model of external reality of its own possible actions within its head, it's able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, utilize knowledge of past events. So this is the idea that a simulation can be something that an agent runs inside its heads, rolls out trajectories, figures out there's consequences, and then takes an action in the real world. And these are three completely independent use cases. You could have a simulator running inside the agent's policy, but it's neither trained in simulation nor tested in simulation. It's just a robot in the real world. And you can obviously have the 1,1,1 combination where all three of these things have been turned on. I think it's important to think of these factors separately, because if you want to design simulators for these three use cases, they require very different considerations. And that's what I want to tell you. What do we need to do in order to optimize a simulator for these things? I will not talk about the third one because I don't yet have any published research on that. I will talk about the first two, but I'm happy to chat about the third one in questions after the fact. So right now, we are optimizing for none of these three use cases. Right now, we're optimizing for humans. Simulators right now are designed by taking video game engines like Unity, putting a Python wrapper around them and feeding it to PyTorch. And this is, for example, the architecture of AI to Thor. And these things necessarily run at something like 10 to 60 frames per second, or FPS. It is because humans do not notice anything faster than 60 FPS. And this is because fundamentally human needs and AI needs are very different. What humans in video game engines need are high pixel resolution. 1080p is nothing. People ask for even higher than that. Humans do not care about anything faster than 60 hertz. What machines need is something entirely opposite of this. Machines will not ask for very high resolution, pixel resolution images, because ultimately these things are all going to feed into a CNN, and 84 by 84 is fine. 128 by 128 is fine. We don't need 1000 by 1000, for example. What machines will need are extremely high frame rates, extremely high rate of generation of observations by the simulation, so that we can have fast perception action loops, so that we can do fast training and testing. Machines will also not just care about RGB, but depth, semantic segmentation, surface normals, audio, GPS and compass, radar, and other sort of simulations. And you want this distributed, running headless on a cluster, as opposed to connected to a monitor for a video gamer. So hopefully that conveys the difference between human and AI needs, and why they are so different, and why you might want to design simulators differently for one use case versus the other. So now let me start into the first thing. If you wanted to train in simulation, what would you want to care about? And I would argue that the number one thing that you care about is speed. So here is, for example, a plot of frames or actions per second. How quickly can the simulator give control back to the agent after an action is taken? And most other simulators, at least till a couple of years ago, Gibson V2 is now a little bit faster. Most other simulators were in the 10 to a couple of hundred regime. Habitat Sim is natively in the 3000, 4000 regime, depending on the scene being rendered. And because we own the software stack, we can run multiple copies of this on a single GPU, and we can, on a single GPU, get to upwards of 10,000 frames per second. And this really matters. It matters when you're, this is 50x faster than other simulators. And I think it's important to say that 10,000 FPS is not just an arbitrary number. Here's a thought experiment that we've done. There are 1.2 million training images in ImageNet. If you just wanted to load them from disk without doing forward prop on a CNN, so in an empty CNN, if you just want to load the batches and go to the next batch, with a parallel loading library and a custom hardware, we could get it down to 180 seconds. That's 7,000 FPS. Most commodity hardware, you will not be able to get it down to this. So what this tells us is that if we are willing to dedicate one GPU to the simulator, we can create images faster. We can render images faster than they can be loaded from disk, and that right there is impressive in how quickly we can train these systems. Let's see. Is having a higher FPS important because it better simulates a continuous environment? I actually want to quickly answer that question. Having higher FPS is important because, not because the environment is continuous and you want to capture it at a high frame rate. FPS is important because what you're really counting are actions per second. There is a perception action loop. So here is, for example, why does speed matter? The speed matters because now you can run experiments that you couldn't before. There is a perception action loop, and so the faster the simulator can hand control back, the faster you can run this loop. And this is the loop where I'm talking about, that if the simulator gives you control back, you can take more actions, and this directly affects training and testing. And so here's a question that we asked in a recent paper that directly affected, that was directly an impact of how fast we could train things. And the question we asked was, how far can we scale model-free RL, reinforcement learning, for embodied visual navigation? There's a question on low resolution of images. You'll see in a second when I talk about CNNs why low resolution is okay. The task that we looked at was point goal navigation. So this is the point goal navigation task. You have an agent that is spawned in an environment that it is not familiar with. The map here is only for visualization. The agent is asked to go to a point in space specified in terms of relative to the agent's start location. So in agent's coordinate system, it is told you have to go 10 meters west of you or something. It does not know the map, so it does not know where the obstacles are. It has access to an egocentric depth camera, an egocentric RGB camera, and it has access to ego motion sensor that tells it how far it has moved, and therefore it can keep track of where the goal is. So it has access to, you can imagine, a GPS and compass sensor that tracks its movement, and therefore it can track where the goal is because the goal is stationary. And so this is the task. This is what an episode looks like. Our agent wakes up, takes a few actions, and it gets to the point. The classical robotics pipeline for this would break it down into 3 steps. There's a mapping, localization, and a planning aspect of this problem. You would say, hey, let's build a map along the way, localize ourselves against that map, establish where the frontiers of what we don't know, and plan a path. We are going to do, we're going to say that this is a lot like where machine translation was a few years ago, where translation used to work by first defining a translation dictionary, a phrase dictionary of like small words that can be translated into other things, and then solving an alignment problem, and then doing re-ranking on multiple alignments. And we are going to say that we're going to do none of this. We're going to do just a model-free approach that knows nothing about navigation, nothing about mapping, nothing about planning, nothing about A*, just nothing. Perception to actions. And we're going to ask, how far can we scale this? And so here's the agent and model design. The model design is, you take an image, and this is where low resolution matters, the 84 by 84. It's just going to get fed into a CNN to convert a representation of this image, continuous vector, and the goal coordinates with respect to the robot's position. These two are fed into an RNN or an LSTM policy. It's a recurrent policy that produces an action like turn left, turn right, and a value function estimate, but we can ignore that for now. And we just unroll this policy out. So far, this is no different than an image captioning model or a visual question answering model. This has nothing to do with navigation. The only place where this intersects with navigation is in the reward function design. We're going to say that we'll unroll a trajectory if the goal is reached. we will give you some positive successful reward. If the goal is not reached, then we are doing some reward shaping, which is the improvement in the distance. So the distance to goal at t-1 minus distance to goal at dt, and a penalty just for encouraging efficiency. That's it. This is the only part where this interfaces with a navigation problem. There's a question about transferring an agent to real environments, and I will talk about that in the later part of this talk. Okay, so let's scale this. We will scale the heck out of this experiment. And so this was a work that we presented at iClear earlier this year. This is called Decentralized Distributed PPO. It is I won't go into details of this, but it is a distributed version of PPO where we launch multiple jobs on multiple GPU workers. Each of them are simulating these rollouts of PointNav and are doing gradient collections for their experiences that they've collected on that. And then synchronizing these gradients in a distributed data parallel manner to then take a update step. And this is a fairly simple implementation in the sense that it is synchronized, so you don't have to do much. And it allows us, what we found is that with a small number of tricks, we are able to scale this very well. So on the x-axis here is the number of GPUs. It's going out to 250. On the y-axis is speed up. This is ideal scaling. This is the best you can do. This is where DDPPO is, and this is where a naive implementation would lie. DDPPO at 256 GPUs provides 196x scaling. So there's another factor of nearly 200 that we've improved over the 10,000 FPS, right? By scaling it to 256 GPUs. And so to answer that question of how far can we scale this, here's what we've done. On the x-axis here is the amount of experience or number of steps that an agent takes. Every time the agent takes a step, it receives a frame from the simulator. And notice that this is going out to 2.5 billion steps, 10 to the 9. On the y-axis is performance or success on this task. This is not training performance. This is validation or testing performance. And we notice that as we train this out, we get near perfect performance. This takes 180 GPU days to train, which was done in 3 wall clock days because we were able to do this on 64 GPUs. And we are able to get near perfect 99.9% success on this task. This right here is about as close as machine learning comes to solving anything. This is generalization on a data set where we're not touching testing environments at all. We're simply testing on them, and we find that we can test on these environments. This is, for example, what this episode looks like. An agent was spawned here. It is only observing egocentric frames, and it is able to reach its target. Notice that we can trivially do things like turn off the depth sensor, and so now it's a blind agent. And the same algorithm applies, and what we see is the emergence of these algorithms called wall following or bug algorithms. These are classical algorithms that were analyzed in the 1970s and including and 80s as well. And there are interesting theoretical papers that show that if you have piecewise polygonal obstacles, then bug algorithms can always solve the task. You can always reach from point A to point B. And what we see are emergence of those algorithms where it goes and slams its face against a wall and then explores right and explores left and is able to, and so this is the emergence of that algorithm. Here is another example of an agent that follows a trajectory. And at this point, the agent, if we look ahead, can see has a few choices. You can go right, straight, or left. The goal sensor is telling it that the goal is located directly in front of the agent. The depth sensor is telling it that there is an obstacle up ahead. On the left is also an obstacle, and the agent naturally just chooses right. It seamlessly makes that decision. We don't even notice that something happened here. And this is an episode of following this. Okay, there's also the emergence of backtracking, where the agent overshoots a particular entrance to a room, then backtracks and goes through and reaches the target. I will skip the visual Turing test because it works well better with an interactive audience, where I try to show two examples and show you that one is a learned agent, one is the shortest path. They really do look very similar to each other. And a typical question I receive is, what if I don't have access to a large GPU cluster? Well, the number one thing is that 90% of the performance is achieved very early on. Notice that the x-axis is in log scale and the curve still exhibits a log-like behavior. So this is really log-log behavior that we're seeing. So very quickly we're mostly done, and that's a good thing if you want to run quick experiments. This can be done in less than a day on 8 GPUs. And as hopefully we think of this as ImageNet pre-training, that our trained CNN models are available. You should just chop off the policy, just take this CNN and use it for your tasks. We found it quite useful to start from this CNN than others, because there's just perception and egocentric obstacle avoidance built into this CNN. So this is publicly available. Okay. So hopefully that answers this question: how far can we scale model free RL? The answer for point goal navigation with an RGBD sensor and a localization sensor, notice that these are strong assumptions, is very far. We can scale this very far. However, not far enough. We've done, if you just remove the localization sensors, then we're down to 40 to 50% success. And if you change the task to object goal navigation, then we're down to 10 to 20% success. So we have a long way to go. And I don't think model free RL is really the approach to get us there. I just believe that it was an interesting scientific study here to ask how far we could go. And I think whatever tasks we do take on and whatever architectures we do take on will require scaling as well. So building these infrastructures out will still be useful. So that was the answer to this question. If you want to train in simulation, I think the number one thing that matters is speed. That's all that matters if you want to train in simulation. The purpose is to generate, that's not all that matters, but that's the number one thing that matters. I do not think, there are other things that also matter, but this is the number one in my view. The other thing I want to get to is testing in simulation. And this will answer some of the questions that were asked by people. So this was a paper that is appearing at IROS this year, and also at Robotics and Automation Letters Journal. Here, what we wanted to study was this specific question. If a method A outperforms method B in simulation, how likely is that trend to hold in reality? And I'm asking this question specifically because I've seen a lot of sim to real papers that tend to emphasize on, look, my pixels look different between the simulation and reality. Look, the physics is different. Look, the collision behavior is different. And I wanted to cut out a lot of that noise and say, none of that matters. The ultimate thing that we care about is, do our hypotheses hold up? What is the point of testing in simulation? The point of testing in simulation is to test hypotheses. Do our hypotheses hold up in simulation as we transition them to reality? If we claim that we're doing model selection or we are making progress in simulation, is that predictive of progress in reality? And I think that's all that matters. Trying to eyeball pixels between simulation and reality, trying to eyeball how physics behaves, is not really the goal here. And I'm happy to take people up if they disagree on that. I'm happy to take that in questions. And if you want to test this hypothesis, the question that you want to ask is, can I run parallel studies? So here is a lab environment. This was in Georgia Tech. We scanned this lab environment using what I showed you. So we created a 3D scan of this, loaded it up into Habitat. And so now what we can do is we can run parallel studies. We can load a robot in simulation, create an episode of point A to point B. We also have that exact same robot in reality in that room. We can ask it to go from point A to point B. We can run the exact same policy in simulation and reality. And what that will give us is a plot like this, where on the x-axis is a metric of performance in simulation. On the y-axis is a metric of performance in reality. The same model and policy is being run in both. And that gives us a point. What you want, if your simulator is good, is for this point to lie on the y equals x-axis. You want identical performance between simulation and reality if your simulator is good. If you want to loosen So on the right, if this triangle indicates that your simulator is easier than reality, and this triangle indicates that the simulator is harder than reality, if that's where those points lie. Now, while y equals x is the goal, you may want to loosen that criteria to say, well, actually, I'm going to run multiple methods. Each one of these points is a different model or an architecture or a policy. And what I really want is high correlation between their orderings in simulation and reality. I want a scatter plot with a high correlation coefficient. You can do rank correlations, you can do linear correlations. There are a number of metrics that can be done here. But really, this tells us that your simulator is letting you make decisions that are correlated with the decisions you would have made in reality. This, by the way, is not where we started. Where we started is this. This is what our plot looked like when we started with the 2019 Habitat Challenge configuration. And what we are seeing here is that a number of methods look like they're performing well in simulation because their x-axis is high, but their y-axis has a big range. Some methods are really bad and some methods are really good in reality, but you cannot tell by looking at their simulation performance. So this tells us that the 2019 Habitat Challenge, if it was rerun on a real hardware, would not give us the same winners. And that was disappointing for us because we ran that challenge. The way we were also able to identify that the culprit is the way we simulate sliding on the robot. And collision checking on the real robot. So this right here is how we had initially implemented. This is a very common behavior in video games, that when you push up against a collider or something that you collide with, you make partial progress and it slides along collisions. On the real robot, there is a collision checker there's a bump checker that actually stops the real robot. And so this is with sliding off. And a couple of changes like that are what allowed us to go from this type of a plot to this type of plot. But formally, like we were fine. We were able to get essentially a formal method of testing what is a good simulator versus what is a bad simulator. Okay, let's see. I just want to keep an eye out on time. Right, we're about. So what I want to say is that if you want to test in simulation, what matters most is sim to real predictivity. Is performance in simulation predictive of performance in reality? And can you trust the outcome of your experiments in simulation? I think we have to be careful about this and always, every so often run sim to real studies. We have found that we can make a small number of changes and now we are able to trust our progress in simulation. But this is something that as we add new capabilities, we would have to test again. Okay. I just want to quickly say that we also have research ongoing in instruction following. So this year at ACCV, we have a paper appearing where we lift vision and language navigation to continuous environments, and another paper where we use web scale data like conceptual captions to make progress on vision and language tasks. I won't talk about that here. I've spoken about that in another talk, and I'm happy to point you to that talk if you'd like to learn more. And ultimately, I'm really interested in this question. I'm interested in building systems. I've done work in visual question answering in images. I've done work in embodied question answering with robots. But I think I'm really interested in like these sorts of systems where the robot is not navigating, but the robot is observing the world from your perspective, and you can answer questions about them. This is something that I think a lot about, and I don't have anything concrete to say, but I'm happy to answer questions about this sort of a direction. There are some pointers here that I hope you'll find useful. And I guess I'll stop here and take any questions that there may be. Thank you.